Yes, class. Am I audible to all? Muniba, Jesleen, Ibrahim.
Yes.
All right. So good evening, class. In the last class, we started with this last topic, conversion of galvanometer into voltmeter and ammeter. And we could only complete a little bit portion of galvanometer. Its structure we saw. And I told you that what's a galvanometer? It's a device that is used to detect current. Okay. So please open the cameras, all of you. And let's start with the class then. Till here we have completed. All right. See class, I was discussing the principle of the galvanometer with you. Principle of galvanometer basically was that the current that flows because of the magnetic field. Here the current that flows and the magnetic field, they give rise to torque. So there are two kinds of torque in your system now. One is the deflecting torque. What is the deflecting torque? The torque that is actually producing the pointer to rotate. So was that? We saw in the last class, remember? NAIB. This was the deflecting torque. Now, in class 11th, we have done that torque is always restoring in nature. Whenever you have forces or torque, they are always restoring in nature. In the sense, they will be always directed towards the mean position. Okay, they'll be directed towards the mean position. So that's why here also you will have a restoring torque. Now, restoring torque formula, does anybody remember from SHM chapter? K theta. Okay, K theta. So here what will happen? The restoring torque and deflecting torque, both are torques. When we equate NAIB equal to K theta, we get the formula for theta as NAIB divided by K. Now, what all are the things that I've written? Theta is basically the deflection here. It's the angle. So angle will tell you by how much did the spring deflect. What was the deflection? By how much angle did the spring deflect? Yes. And N is the number of the turns that we earlier also saw. This was the number of turns. A is the area of the coil. I is the current. D is the magnetic field. These things we've already seen in the torque part. Now, what is this K? K is basically a constant that we say torsion constant. We call this constant as a torsion constant. This constant basically acts here in order to see, you can remember it like the SHM's constants we had for various figures, for various cases, we had different values of these constants. So this is that constant. Okay. Now, you are going to, whenever somebody asks you what's the formula for the deflection, by how much did the pointer get deflected? So you'll always say this deflection is NAIB by K. That's it. This is the whole derivation, this one line derivation. You should just know there's a deflecting torque that is acting, which is rotating the pointer, and restoring torque will bring it back to its mean position. That's it. This is what you should know and the formula. Now, coming to a small topic, that is sensitivity of a galvanometer. What is the sensitivity? So in usual terms also we use the term sensitive. In our common language also we use. So when do we say a person is sensitive? When the person reacts more for a very lenient thing, right? Then we say, okay, the person is very sensitive. So here also in case of galvanometer, if for a very small amount of current, there's a small amount of current in the circuit, the galvanometer is giving a very huge deflection. Then we say, okay, galvanometer is very sensitive. Even it is able to detect a very small amount of current that is flowing through the wires. So sensitivity of galvanometer is what? Galvanometer is able to detect small values of the current. So even for small values of current, the galvanometer will give you large deflections. This is what is meant by the sensitivity of the galvanometer. Now, there are two kinds of sensitivities that are present. One is the current sensitivity, other is the voltage sensitivity. What is the current sensitivity? current sensitivity is basically deflection per unit current. Whatever is the deflection per unit the current. Means if I say current sensitivity, whatever was the deflection theta divided by the current. Now, what was the formula of theta? Look, NAIB by K. So I'll put it NAIB by K. And in the denominator, we'll have current I. Current gets cancelled. IS is equal to NAB divided by K. This is the current sensitivity. What is voltage sensitivity and what is the meaning of it? Actually, physical meaning of current sensitivity is that only that for small amounts of current, the galvanometer is giving you huge bizarre reaction that yes, the deflection is more even for a small amount of current. So what is voltage sensitivity? Voltage sensitivity is deflection per unit voltage, theta divided by the voltage. Now, according to Ohm's law, we know what is V? It is equal to I into R. Now, let's put the value of theta. NAIB by K. And here we have I into R. Current will be cancelled. What is Vs equal to? NAB divided by K into R. This is voltage sensitivity. Okay, how is voltage sensitivity then influencing? Because voltage is not related to the galvanometer directly. It is related in the sense the voltage will affect the current, and again the current will affect the galvanometer to detect. So smaller amount of current will give you larger values. Larger values in the sense it won't give you a fixed value like the ammeter, but it will show a large deflection. That is what is meant by galvanometer is sensitive. We have this. When we say resistors are sensitive, rheostat is sensitive. These terms are often used. We often use rheostat is sensitive. So even for a small change in the rheostat, a huge resistance is being provided in the circuit. So sensitivity of devices are there. So one such is the current sensitivity and the voltage sensitivity. We'll come to the next topic, which is actually the topic conversion of galvanometer into voltmeter and ammeter. But for that, you should understand the galvanometer. This part comes in the exam. Okay, this part comes in the exam. Sensitivity is not very important, though it is there in your textbook NCRT, but this isn't very much important. It didn't come in the exam till now. Okay. So out of all these ammeter and voltmeter ones are very important, and the galvanometer ones are lesser. Okay, got it? Is that clear?
Yes.
What about others? Ibrahim, Jasleen?
Yes, ma'am. Like my face.
Zainab, did you get it? You joined a little late. Were you able to understand? Zainab? Please let me know if any part has to be repeated. Okay. All right. Please write it, all of you. All right. See, using a galvanometer, when you have to get the values of current, ammeter does what? Ammeter is a device that measures the current. Exactly. As we discussed that it gives you exactly the value of the current. But what does the galvanometer do? It just detects it, whether yes or no, a current is present or not. So when we're talking about the conversion of galvanometer into ammeter, it means you just have a galvanometer, you have a resistor, and arrange them in such a manner that you are able to get the values of current. So how is that possible? It is done using, what we do is we take the galvanometer, let's say the resistance of the galvanometer is G, and we connect a resistance in parallel to it. What is this? This resistance is basically called the shunt. So shunt is given, the term shunt is given, but it is the resistance only. So this is what is meant by the shunt. Shunt is, see, there are two characteristics for a shunt. Remember that this has to be connected in parallel only to make it into the ammeter. If you connect it in series, then it won't give you the exact value for the current to convert it into an ammeter. Okay. Second is that the value of this shunt should be small. Okay, it shouldn't be a very high valued resistor, a value with a small amount of resistance. This is what is shunt, this is what is the galvanometer. Let's say some amount of current I entered. So let's say the amount of current that went through this galvanometer is Ig. So yes, someone, Ibrahim, yes, how much current will be here?
What one?
What will be the current here?
Through the resistor or through the galvanometer?
To the shunt, Ibrahim, were you not listening?
Oh yeah, true. So no, mama. I was reading actually.
Shunt.
So ma'am, current. So I is equal to S. V is equal to IR. So I will be equal
No,
to V.
Ibrahim, no. See, I said, listen, I amount of current is coming. Ig amount of current goes through this galvanometer. How much is left to go into the shunt?
I minus Ig.
I minus Ig. Okay, yes, right. See, class, I minus Ig will move through this shunt. Now we'll have the Ohm's law and everything that we study. First, let us just distribute the current. Muniba, can you tell me, will the voltages across the shunt and the galvanometer, will it be same or different? Muniba? Same, yes. Because it's connected in parallel. So potential difference across the galvanometer will be equal to the potential difference across the shunt. Now let's apply the Ohm's law. Okay, see here the current is Ig, resistance is capital G. So according to Ohm's law, can we say the potential difference is Ig into G? Coming to the potential difference here, the current is I minus Ig and the resistance of the shunt is S. So here we'll get I minus Ig into S. So sometimes you need to calculate the value of this shunt. So from this simple equation, you can now calculate anything. You can calculate the value of I, you can calculate the value of Ig, anything. So S will be equal to Ig into G divided by I minus Ig. Yes, tell me all of you. Have you got this formula? This is the formula for the shunt. This is a resistor which is connected. So this is important. Sometimes the characteristic is also asked, characteristic about the shunt to convert the galvanometer into ammeter. Okay, yes, is it clear to all? Muniba, Ibrahim, Jasleen, Zainab?
Yes,
Oh, all right, fine. Please write it. Then let's see voltmeter 1. First write down this one. Done?
No, mom.
Yes, done now.
Yes, ma'am.
Okay, look, now coming to conversion of the galvanometer into voltmeter. So what do we do here? This is our galvanometer with the resistance G. We'll connect a resistor in series this time of our resistance. Shunt means whenever you are bypassing something. That's why we wrote shunt for that. This is a simple resistor, but again, two conditions for this one. One is that this has to be connected in series. Second is that the value should be very high. High resistor should be connected in series. And again, we'll say, let's say the amount of current that is flowing through this is IG. Now let's apply the Ohm's law. According to Ohm's law, we know that V is equal to IR. Now this is not a single resistance. Here we have R equivalent, right? So see, when you have R equivalent, Jasleen, can you tell me what will be the R equivalent in this? Two resistors are there connected in series. So what should be the net resistance? R equivalent. Yes, Jasleen. What's the net resistance here to apply Ohm's law? No. Zainab, can you tell? V by I. No, Ibrahim, you've answered for parallel. Zainab, that is right. But from here, what is R equivalent? From here, this is one resistance, capital G. One resistance is R. They are connected in series. And what's the equivalent capacity? What's the equivalent resistance? Yes, Muniba, correct. Now you're right, Ibrahim. R plus G. Two resistors are there. I think this was the easiest question of all. Yes, it will be G plus R. So see, when you put in this value, V is equal to, now what's the current? It's IG. And what's the resistance? G plus R. Now, if I shift this here, if I write what's the value of G plus R, I'll get V by IG. This class, I'll get V by IG. Now, look, what do we have to get? We have to get the value of the resistance. So what will R be equal to? This is an addition here. So here it will be subtracted. So V by I, V minus G is the formula for the resistance here. Formula of resistance I am writing, but whichever variable is missing that you will calculate. So using just a galvanometer, you will be able to get the voltage as well from the formula. V can be calculated. From here, current I can be calculated. Okay, so that's what we have. My voice is coming very low. Is it to all? Yes, someone please confirm. Ibrahim, Muniba?
No, ma'am.
No. Zainab, then it must be some network issues. The volume is fine to others. Okay. So see here, R is equal to V by IG minus capital G. What is this? From here, I was saying, Zainab, that we can convert galvanometer into voltmeter. How? Look, if from using this formula, I can get the value of the voltage, if I know the rest of the things, I'll get the voltage without having an actual voltmeter. And look, without having an actual ammeter, I can get the total current using this, if I know the rest of the things. And other than that, you can calculate the shunt, you can calculate the value of the resistance as well. Now is it clear to everyone? Jobita, you and others got this topic? Okay.
Yes, ma'am.
Okay. Write it, then we'll practice a numerical based on this. Please write it. Done, class? Completed? See, this question says an ammeter of resistance. When it says ammeter, this means this is referring to the galvanometer that has been converted. So ammeter of resistance 0.8 means resistance of the galvanometer is given to us as 0.8 ohm. Okay, this can measure currents up to 1 ampere. Now, if the galvanometer is measuring certain amount of current, so what do we call that? We call that as Ig, right? We used to take the current through the galvanometer as Ig. This was 1 ampere. This says what must be the shunt resistance to enable the ammeter to measure the current up to 5 ampere. Means the current in the circuit is given as 5 ampere. It says what is the value of the shunt so that all these things can be in line. So one formula we studied, S is equal to I minus Ig into G Ig by this was Ig into G divided by I minus Ig. This is the formula, class. Now look, let's put in the value. S is, what is Ig given? 1 ampere. Galvanometer's resistance 0.8 divided by current is 5 and Ig is 1. So this becomes 0.8 divided by 4, which is equal to 0.2 ohm. This is the shunt resistance. First tell me, is the first part clear to all?
Yes, ma'am.
Okay, let's come to the second part. It says what is the combined resistance of ammeter and shunt? Means this, what is our ammeter right now? Ammeter is basically the galvanometer and there is a shunt. It says what is their combined resistance. Now, Ibrahim, the one which you were answering here will be applicable here. Look, they both are connected in parallel, shunt and galvanometer. So now your formula will be used, right? So here the combined resistance means the equivalent resistance. 1 by R equivalent is 1 by capital G plus 1 by S. Okay, so that makes it S plus G divided by S into G. So our equivalent is equal to S into G divided by S plus G. So here we'll put in the value. This is 0.2, that is 0.8. Our equivalent will be 0.2 into 0.8 divided by 0.2 plus 0.8. So this is 0.16 divided by 1, which is 0.16 ohm. This is the total combined resistance of shunt and the galvanometer. It's a very good question because it's not written in complete straight words unless you decode it properly. Calculation part is very easy, but the language of the question is a little tricky here, especially to identify that this is G. This is capital G, which is the ammeter of resistance. This is given like this. Okay. Now, is this whole topic clear? In fact, the whole chapter, is it clear to everyone? This completes with the chapter 4th. Yes, Jobita, Ibrahim, Jesleen, Muniba, Zainab, response. Is it clear?
Yes, ma'am.
If anything is there that you want to ask from this chapter, please let me know. After this, I'll start with chapter 5th. Okay, all right, fine. Please write it, class. Yes, class. So all of you pay attention. Now let's start with the chapter 5th. So this is chapter 5th, which is magnetism and matter. Okay. Now, see, we'll be mostly focusing on the bar magnets, its properties. So, as it's written in the introduction, that here we deal with the natural magnets and the permanent magnets. See, class, natural magnet means earth magnetism. Earth's magnetism. Earth's magnetism means that as if this entire earth was replaced with a very big bar magnet. But class, this has been deleted